Okay, I think we can proceed with the next speaker, Claas Abert. Claas received his PhD at the University of Hamburg, working on micromagnetism as far as I remember, right? And now he's with the Technical University in Vienna. And yeah, I'm looking forward to a special perspective on a data scientific problem now. Let's welcome Claas.
Thank you very much for the kind introduction, and thank you for the opportunity to speak here. Topic of my talk will be scientific computing with Python, and I'm mostly dealing with continuous problems. So I have to say that I'm not like you guys, a creator of the Python language or stuff like that, but just a simple user. So the whole talk will be from the perspective of a scientific Python user, and the Python stuff will be pretty basic, I guess. So let's come to the outline of my talk. I will start and give an introduction to magnetism and how this is connected to partial differential equations, because that's kind of my research topic in Vienna. And then I pick out two methods for the solution of partial differential equation. One would be the finite difference method, and I will show how to apply this method with Python and what problems arise. And in the last part, I will give a short introduction into finite elements and some tools we are using to solve partial differential equations with finite elements. And finally, I will conclude. So a bit about me. As Philip mentioned, I got my PhD in Hamburg, and since 1 year now, I live in Vienna and still working on micromagnetism. That means we are developing simulation software for magnetic nanostructures and spintronic devices. And in particular, I'm interested in numerical algorithms for the solution of partial differential equations. And yeah, my work is partly funded by a company in Finland. And as part of this collaboration, we are developing and trying to improve magnetic sensors, especially for automotive applications. So let's start with a brief introduction into ferromagnetism. As you might know, from school, ferromagnet consists of a large number of elementary magnets, and you can think of these elementary magnets as tiny compass needles. So these are dipoles, and all these elementary magnets interact with each other through different mechanisms. And yeah, on the next slide, we will have a look at these different contributions which make the magnetization move in time. So the most simple contribution is the so-called Zeeman energy. So every magnetic dipole likes to be aligned in parallel to an external field. There's supposed to be a large arrow, so the external field points in this direction, and the elementary magnet likes to stay aligned in parallel. Anti-parallel would be very bad for the energy. So the next contribution is called demagnetization field. So as I told you, every elementary magnet is kind of a small magnetic dipole, and that means it not only moves in magnetic fields, but it also creates magnetic fields, in this case the dipole field. This is, okay, you can see that here, very slight magnetic field lines. And yes, in these fields generated by this magnetic dipole, every other elementary magnet tries to align in parallel again. So that means the field line goes like this. So if I put another elementary magnet here, it tries to align anti-parallel. And so this coupling is bidirectional. That means this magnet also creates a field, and this acts in the field created by the right elementary magnet. And if you now put in more and more magnets, if you put in more and more magnets, you will see that configurations are energetically favored that have closed flux lines. And that's why this contribution is also called demagnetization field, because it tries to demagnetize the whole magnetic body. So if there was only this interaction, we wouldn't have macroscopic magnets. This is where the exchange interaction comes into play. And the exchange interaction is a quantum mechanical effect, which prefers neighboring elementary magnets. And that means elementary magnets whose wave functions overlap. And these neighboring magnets are have a lower exchange energy if they align in parallel. So this is a very local field. And now the interesting part in magnetism is that we have this competition between the global demagnetization field, which tries to demagnetize the whole body, and a very strong local field, the exchange field, which tries to get a homogeneous magnetization configuration. So it's kind of a multi-scale problem. If we want to simulate large structures, we not only have to take into account the global interactions, but we also have to look very closely in detail how this short-range interactions take place. So how do we compute such a structure? If we look at the body of, say, size in the micrometer size, it consists of like 10 to the power of 23 elementary magnets. So this is obviously not a number we can handle with a computer. What we do instead is we make a model which is continuous. That means we start with a discrete model, go to a continuous space, and now we try to solve the problem in this continuous space. But until now, we started like with 10 to the power of 23 degrees of freedom, and now we are in a continuous space. That means we have infinitely many degrees of freedom. So what do? We still can't compute it. So we have, again, to discretize the space, and we do this by creating a mesh. And this mesh can either be a simple regular grid like this one, or it can look like this. And depending on the method we are using, we are able to handle more complex or more simple meshes. So what did we gain by going from the discrete to the continuous back to the discrete? First thing we gain is that usually the discretization we need in order to compute this model can be much larger than the resolution of the elementary magnets. So we have less degrees of freedom. And on the other hand, our model now is described by partial differential equations, and there's a very well, a very good numerical framework to solve such kind of problems. So we can rely on many mathematical methods and so on. Okay, this is a real-world example, which we are able to simulate with our software. It's a write head of a magnetic hard drive, and it consists basically of three parts. The first one is an electric coil, so a current flows through this coil and creates an electric field. Then the second part is this one. This is the magnetic material where we want to write our bytes. And then there is this yoke, and this soft magnetic yoke guides the magnetic flux to the pole tip, which you can see here. And this pole tip is very small in order to create very local fields and in order to write small bytes. And the whole writing process looks like this. So the current in the coil is switched in direction, and as you can see, magnetization flux goes through the yoke and is able to write a byte. Okay, so how do the problems we have to solve look like? This is a brief overview over the micromagnetic model. As you can see, there are many coupled differential equations, and it looks kind of scary and complicated. And in order to show you how to solve these problems with Python, I decided to focus on a more simple problem, and this is kind of the mother of all partial differential equations, and it's called Poisson's equation. This is the Laplace operator. This is the solution we are looking for, and this is some right-hand side, and I will try to try to do as less math as possible, but I thought as kind of motivation, because that's the part I'm coming from, it's maybe good to have some equation, and yeah, in the following there will be less formula. So as I told you in the beginning, essentially I will show you two different methods to solve such a system, one of which is the finite difference method. And in finite difference method, we always have to act on these regular grids. And as you can see, this is not so good if we want to describe curved structures like the circle. So we get artifacts on the edges. But a big advantage of this method is that we have a couple of very fast algorithms. So if we have simple geometries, it's always better to go with this method. If we have curvature and complicated structures, we use the finite element method. And as you can see in this method, we can use irregular grids. And yeah, one of the big advantages, as you can see, is that we can model the curvature pretty good, even with relatively large simulation cells. Okay, let's start with the finite difference method. The solution we are looking for is a continuous solution, but as I told you, we have to do some discretization somewhere. So how do we do that? Let's look at some continuous function u and try to discretize it. And if we have a regular grid and if we consider a one-dimensional example, the discretization is straightforward. So we have a regular grid, and we start with a continuous function which has a value at any point x. And we transform it into a vector, which has an indice I. And so ui is just defined by the value of the continuous function u at the point xi, and xi is chosen to be equidistant. And so this is how we get some continuous functions into the computer. The next question is we want to solve differential equations. That means we somehow have to discretize our differential operator, and in this case it's the Laplace operator, and in n dimensions the Laplace operator is given by the sum of the second derivative in the different spatial dimensions. Now we are in one dimension, so the Laplace operator simplifies to just the second spatial derivative. And what we do now in finite differences is that, as you might know, the derivative is defined by like infinitely small differences. And what we now do is we don't take infinitely small differences in order to get like the slope of our function, but we just approximate it by finite differences. And that means we can approximate the second derivative at the node I by taking the values of neighboring cells with some weights. So this has a weight +1, obviously. This has a weight -2, obviously, and this is +1. And then we divide by our spatial discretization constant h. So h is exactly the width of one interval here. And this is a very simple approximation of the second derivative. And so with this tool, we have everything we need in order to compute the solution to a Laplace Poisson equation in one dimension. So what features does our programming language has to have in order to solve such a problem efficiently? We want to be able to deal with very large data sets, maybe not that large as your data sets, but at least we want to be able to like describe systems with, say, millions of nodes. We want to be fast because we are interested in the time evolution of the system. We want to be able to like simulate the system not only for split seconds, but for longer time ranges. So we just need speed. Most of the operations we need are a kind of single instruction multiple data. So the language should be able to handle these kinds of problems well. And it would be nice if we also get some parallelization where possible. What we don't need is redundancy or fail safety, because if a simulation fails, we just start it again. And we don't need real time. There's no data coming in. We have to store and we have to keep forever or whatever. So we are just interested in if we have a start configuration of a magnetization and we define some external fields or so, we are interested in what happens, and if a simulation fails or takes too long, we just do it again or just wait another month for the results. Okay, so why did we choose Python for these computations? Python has a concise syntax, and usually Python code is very readable. And in this context, Python is very well suited for building kind of domain-specific languages. So we can like create an API for our physical problems that reads a bit like the problem itself. So this is a nice thing to have if you collaborate with other physics students or so, that they really can capture what the code is, what the code is doing. Another big plus of Python is that we have IPython. So for prototyping and for trying out new libraries, we have an interactive thing where we can fast try out new stuff. Then this is a bit controversial. Python is dynamically typed. This is one of the reasons why the syntax is so brief. But on the other hand, there are sometimes problems. So I personally like these dynamically typed languages because of the brief syntax, others don't. And the last and most important part for us is it fast. And as it's dynamically typed and as it's an interpreted language, we probably might run into performance issues for some tasks. So I put the speed on the minus part here, but with a question mark. So let's have a look at how Python performs compared to C. And we start with a simple loop. As I told you, most of the operations we do is single instruction, multiple data. So this is kind of the most simple instruction we can do. We just start with a vector with 1 million entries, and we want to multiply each entry with 2, and we do this 10 times. And in Python, a for loop looks like this. So we loop over the range of the length of the index, and then we multiply each entry by 2. And the exact same thing in C here. We have I have an outer loop. I do the thing 10 times so that the time measurement is meaningful and it's not too fast. So almost the same code. Let's look at the execution time. Python is pretty slow. So obviously, if we perform this operation by using for loops in Python, we get a performance. We get a 70 times worse performance than in C. So what do we do about this? We just use a library which is able to handle these kinds of problems. And yeah, you all will know the NumPy library, and I got some bullet points from their homepage. So they claim that NumPy has a powerful n-dimensional array object, tools for integrating C and Fortran code, and linear algebra, Fourier transform, and random number capabilities. So this sounds like something we can use to solve such kind of problems. And specifically, the first point might be important for the thing we want to do. And now we that's too bad. Now we do the same thing as before, but using NumPy to multiply each element with 2. And if we have a NumPy array, we can just perform the same simulation without a for loop by just applying the multiplication directly on the object. And NumPy does the iteration over the objects. And this is supposed to be much faster. And if we look at the execution time, we can see that indeed the NumPy performance now is close to the C performance. It's exactly the same, actually. So the first rule, obviously, is avoid for loops in Python. If you if you want to do computational physics and try to use some collective operations on the NumPy arrays. Here's some more information on how we use NumPy. So if we want to compute the finite difference for a one-dimensional array, so let's try to translate this expression to NumPy. Then we can use the slicing capabilities. I don't know if, can you read this? Or is it too? Okay, but maybe if you are familiar with the slicing, then we can compute this for every element by just copying the array 3 times and like shifting it with the slicing operations, multiply this one by 2, and then add the arrays, and then we get the computation of the second derivative for all elements at once. And this is not only fast, but this is also very elegant because this really looks like the expression we are trying to code here. So then the next thing, until now we just moved in 1 dimension, but we want to move to 3-dimensional structures sooner or later. So it's very nice to have these n-dimensional arrays. And yeah, you can create them like this, and you can access them, and you can also slice each dimension individually. And every operation that NumPy supports has an axis argument, so you can sum up only one axis or do an FFT in only one axis or in all axes at once and so on. So this is very nice. You can do plenty of stuff on these n-dimensional arrays, and it's all very fast. And if you need more sophisticated algorithms and more like specific algorithms, then there's an extension to NumPy called SciPy, and SciPy has things like optimization algorithms, numerical integration, solvers for eigenvalue problems, sparse matrix representations, and so on. So a pretty complete toolkit for solving our kinds of problems. And if this is even not enough, then SciPy has kind of a plugin interface, which is called scikits, and there are many scikits for very specific purposes. Okay, so sometimes you just can't avoid to have these for loops. And now the question is, how do we deal if we really have to use for loops? And this is also an example from the Poisson equation. It's not really important to get the whole formula here, but one possibility to solve Poisson's equation is by a so-called Green's function ansatz. And so we get the solution by a sum of this Green's function expression here times the right-hand side. And the question is, how do we assemble the Green's function G? This is obviously some kind of vector, and it has a pretty complex expression. So it would be very natural to just loop over the indices here and then perform these difficult computation and put it into a vector, and then we can use NumPy to deal with this vector. And yeah, there's a nice library called numba, and numba has the ability to translate simple Python functions to C code and do a just-in-time compilation and call the C function. So we can just create a function, which I called loop here, which performs a simple loop and then does some complicated computations here. I kept in the simple ×2 computation in order to do performance measurements, but in this part you could also do numerical integration or some pretty complicated stuff. And yeah, let's look again at the performance. There's another library called Hope, which does essentially the same thing, which is pretty new. And yeah, as you can see, using the just-in-time compiler of numba gives us a 4 times slower execution time than in C. That's not too bad because we come from a factor of 70 and now it's only a factor of 4 or so. And Hope is even faster than C, and I have no clue why. I think maybe they do some parallel computations. But Hope seems to be really good, at least for simple stuff. lesson learned here is if you can't avoid for loops and you want to stay in the Python world and use simple Python syntax, you can try to use number or hope in order to speed things up. Yes?
Did you have a look at PyPy as well? I don't really know so much about that, but like it has some usability as well.
I read about that. I never tried it. I guess that I use number and hope because it's deadly simple. You just have to write this, how's it called, decorator JIT. And this is just a plain Python function. I guess that PyPy's syntax is a bit more complex, but I'm not sure.
As far as I understand, it's basically just a different implementation of Python, so you would still use exact same.
Ah, okay. So then maybe I tried it.
Python just-in-time thing for Python. There's probably lots of people in this room that know more about it than I do.
Okay.
If you do, speak up, please.
Well, the problem with PyPy is that for the libraries that use C code or Fortran code, you have to have a special implementation for PyPy.
Yeah, they support most stuff with NumPy now, don't they?
Yeah. But if you use anything
If you have
else,
custom
then-
code, then you don't. Yeah.
or if you use
Okay, yeah.
it's not available.
So hope is just a library that does a runtime compilation of this piece of code? Or?
Yeah, actually, it has to translate this somehow, and it has to do complicated stuff like guessing types and so on. And then, yes, it generates C code and compiles it just in time and calls it just in time. And the compiled thing is cached, so if you run the same program twice, it's pretty fast. Okay, more questions on that topic? Then I'll proceed. If this is even not enough, you can always go for native implementation. So you write your own C code and try to make it callable from the Python side. And the easiest, no, it's not the easiest thing, but the most natural way would be to use directly the Python C API. Advantages are that you don't need any additional libraries and you have very fine-grained control over what you're doing. The downside is that it's, I guess, pretty complicated and you have to write lots of boilerplate code, as I have read. I actually never tried this myself. Then another possibility is to use Swig. Swig can actually turn a complete C++ library into a Python library with exactly the same API. And you only have to give some hints to Swig how the types are connected to each other and so on. But sometimes it's a bit tricky to get the right type conversions. Another advantage of Swig would be that it supports more than Python. So you can also create Ruby bindings, as far as I know, and some other languages. And then the third thing I wrote down, but I never actually tested it myself, but I wrote it down because recently in the scientific community, scientific computing community, many people starting to use Python. And as far as I understand, you kind of write your C extension with a special Python syntax, and you can also link C libraries in. So this seems to be the cool stuff right now, as far as I know. And there are more possibilities. So there actually, are many ways to get your C code run in Python. Okay, this is just a small advertisement slide. So we have a finite difference code which runs on CPO and GPO and uses NVIDIA CUDA for the GPU computations and also has NumPy headers and complete Python interface, and this can be found here. Now for the last section of my talk, I want to give a very brief introduction into finite elements. Again, consider the Poisson equation, which looks like this. And in finite elements, the discretization is not done by discretizing the differential operator, but by discretizing the function space. And we have to start turning the original problem into a variational problem. I just give a very brief overview. So we start integrating over the equation and multiplying by so-called test functions. Then we have to transform the problem by integration by parts so that we avoid second derivatives. This is done here. And then the right-hand side is also just integrated, multiplied with test functions. And then, as I said, we discretize the function space. That means we take our mesh as a construction rule for our discrete function space. And so every node belongs to one degree of freedom of this new function space. And if we do all this stuff, we end up with a simple linear system of equations. So we have a matrix times a vector, which is our solution, equals some right-hand side vector. And obviously, this is a bit more complex than the finite difference part. And the challenging task is to transform these integrals into matrix entries and vector entries. And yes, we use this project. This is a finite element toolbox for Python, so to say. And it has a very easy domain-specific language for the description of these variational problems. So essentially, you can see here, maybe I skip back. So this integral becomes somehow the matrix. And in this integral, we have gradient u times gradient v, and then integrate over whole space. And as you can see, the Phoenix guys managed to come up with the domain-specific language that really looks like the mathematical problem. So we have an inner product of gradient u times gradient v multiplied by an integration measure. And what happens under the hood is very complicated and takes this just-in-time compilation approach one step further, because this code is actually translated. This is shown on the next slide. This form language, as they call it, is actually transformed by a so-called form compiler to C code. So there is a code generator that produces optimized C code for the assembly of the matrices and the vectors. And then this C code complies to a certain interface. And then another component of this library is able to use this assembly code in order to really assemble the matrices and vectors. And then there are adapters for different linear algebra backends. So we can also switch between the most popular linear algebra backends to solve the whole system. And this is just, this is some of the code that is generated by Phoenix. So we start with the definition of this bilinear form, this gradient u times gradient v, integrated by dx. And what the form compiler does is it produces actually a lot of functions that are able to compute different things, but this one is the central one because it's responsible for computing the matrix entries. And as you can see there, the code is even pretty beautiful, and it's really fast if it's compiled. And that's currently our main focus to develop finite element software. And this is another advertisement slide. So we also have a finite element code, which is open source and which can be found here and which heavily relies on the Phoenix library. And again, almost every scientific library you will find will have some kind of NumPy bindings. If it has Python bindings, it also has NumPy bindings. And this is very handy because in the case of Phoenix, we can use the NumPy interface to interface with other libraries. For example, we don't only use the finite element method, but also the boundary element method. And there is another library that also has NumPy bindings. And so we can just use NumPy to exchange data between the different libraries. Okay, and with that, I want to conclude. So we chose Python as language because of its concise and very readable syntax. I showed you that pure Python code, for example, for loops might have performance issues, and it's best to use NumPy for these kind of problems and try to always go for collective operators that, so you avoid for loops. Then I showed you that if you can't avoid for loops, there are tools where you can stay in the Python world but get more or less the performance of C. And I showed you some possibilities how to like get your C code run in Python. And yeah, then many scientific libraries have some kind of NumPy support. So this is really kind of a standard nowadays. And this is our homepage where you can find the software we are writing and some other stuff. Thank you.
Is your field of research in these like discretization methods, or is it just a necessary evil for solving your particular
I think it's more or less the second, but yeah.
There's also symbolic mathematical packages like NumPy and Theano, which basically do that as far as I understand. Like they allow you to do continuous computation. And they take part of the actual computation.
You mean as an alternative to numerical methods for the solution of the PDEs?
They do numerical methods, but you type in symbolic mathematical functions and
yeah.
they do all.
But actually the PDEs we are solving, they are not solvable with analytical tools. So you have to go for the numerical approach.
Yeah, they do numerical. I don't know. Maybe we can take a look. I'm also not an expert, but Theano, they.
Okay, I know of some. I know that there are guys who use the symbolic mathematics, for example, to compute the matrix entries of these finite element matrices, because there you have to perform integration on triangles, and you have pretty simple functions, some linear functions or quadratic functions, and sometimes there are analytic expressions, and these libraries are able to compute them. But usually this is done with quadrature rules, so everything is approximated.
One question also in this direction. I've learned also from Theano that there exists some automatic differentiation, but I do not know if it is applied or applicable for electromagnetics. So that's something in between symbolic and.
Yeah. I think that automatic differentiation doesn't really help to solve partial differential equations. However, there are special problems we are looking at where you have, for example, you might have a pretty complicated expression for the computation of the energy of a system, which depends on the magnetization, obviously, in this case. And then it might be, you can use automatic differentiation in order to derive this by the magnetization, which you might be not able to do with paper and pen because it's really long formula. And this has some value because this can be used in order to construct minimization algorithms, for example, but actually I'm not an expert in this automatic differentiation topic, so I don't really know if this, yeah?
So I think the speciality of your library is also the discretization, right? So to what extent can you change the interaction terms? Is that possible at all, or is that more or less just dedicated to your specific use case?
So this Magnum FE by now is a pure magnetic library. But like if you say you want to solve the Maxwell equations or so, then you could, I guess, directly use this Phoenix library if you have to convert them into variational formulations and so on. So the code I wrote is pure magnetic stuff, but this Phoenix library is pretty high level, and you can, with only a few lines of code, you can solve a lot of partial differential equations.
Do you do anything specific to resolve the multi-scale issue of your problem, or do you just have all the PDEs and solve the combined system equation?
Okay, so I guess so we have to look at the very microstructure in order to resolve the exchange field correctly. And the problem with the multi-scale thing is that if it was only for the exchange interaction, we could parallelize the code pretty well, because then you only have next neighbor interactions, and you can just divide your mesh into chunks and like compute every chunk on a different core, and then you only have to take care of the interfaces between chunks. So the problem of the multi-scale problem is that by the demagnetization field, every node is coupled to every node. So we do take care of it by trying to find fast algorithms, but you always have to resolve this, that every node is, so there are tree codes, and there are many different possibilities to try to get this fast. But the main problem is of this multi-scale issue is that parallelization is difficult because every node is coupled to every node.
But your mesh size was larger than the small scale.
Where?
I just got the impression that you.
Okay, so.
So the mesh size is small enough to resolve also these problems.
Yeah, so usually you have to choose the mesh size to be, there's a rule of thumb. There's something called the exchange length that somehow gives a measure on which scale this exchange interaction takes place. And usually you have to use mesh sizes below that in order to get meaningful results. Another possibility is to use, there's work done on using other models which may use coarser meshes where you don't resolve the exchange interaction but go for macroscopic Maxwell equations. Then you are allowed to take, but this is, yeah, that's another thing. Yeah.
Can you say anything about the meshing? What domains do you consider? What are the conditions you impose on the domains?
About the meshing?
Mesh.
Matching or meshing?
Mesh.
The meshing.
The meshing, the discretization of the domain.
There are many tools, so we don't write our own meshing tools. Actually, if you have complicated geometries, meshing is really like a science of its own. And in fact, yeah, it's not, you don't only need a fine enough mesh, but also things like very steep angles are bad for the methods because you get matrices that are close to singular and so on. So meshing is a big issue. We just use software who does it for us.
Is there a Python element?
No, not at all. No, we have other tools and they just write out some files and then we can read in the files with our Python tools. So the meshing is not done in Python.
So the meshing only depends on the geometry and not on the interaction itself.
I mean, if say you could have a body with different materials, right? And then each material would have another exchange length. So you could have coarser meshes in one part and finer meshes on the other part. And also maybe there's a region of interest where you really want to do things right, and then you will choose your mesh to be very fine at that particular region.
More questions? If that's not the case, it's time.